Chapter 7, slides 41 through 49. Okay, so now we have looked at two new mechanisms for substitution, SN1 and SN2. If you're given a reaction and you're being told, hey, perform an SN2 reaction on it and determine what the products are. This is kind of nice because they're telling you, hey, do an addition problem. Hey, do a multiplication problem. You know those math problems where they give you a scenario and you've got to figure out which function to apply? Do I have to divide those numbers or add the numbers? You kind of have to think about the problem itself, right? Those word math problems. They don't tell you 5 plus 3, solve it. They say, you got 5 apples. And, Susie comes around the corner and provides 3 more. And so it's a word problem. So you have to recognize within the word problem that they're asking you to do addition. Well, oftentimes you're going to be given a starting material and a reagent. And you're going to have to step back and understand if the reaction is going to undergo SN2 or SN1, because you know what? You won't be told. So let's just consider a couple points. The electrophile, right? The alkyl halide. If we have an alkyl halide, right, or an electrophile, and the alkyl halide changes, right? Maybe it's a methyl halide or a primary halide. It is most likely that in that case, you're going to apply an SN2 reaction. If you have a vinyl halide, right? So an example of a primary halide could be something like this. That's a primary halide. A vinyl halide is something like this. The halogen's right off of the double bond. It's at the vinylic position. You are not going to do SN1 or SN2 because those cannot be performed on a vinyl halide. The orientation of the orbitals is not in the appropriate trajectory. Let's skip the middle. If you have a tertiary halide, something like T-butyl chloride, then you're most likely going to be performing SN1. Or a tertiary allylic halide, it's tertiary and it's allylic, definitely on the SN1 side over the SN2. Remember, we're balancing for the electrophile steric hindrance, which is you're trying to avoid steric hindrance for SN2, thus tertiary systems are no good for SN2. And you want to also avoid making carbocations that are unstable, namely primary ones or vinyl ones, so you're going to avoid those types of situations for SN1. It's very tough in the middle, right? You can't just look at one thing in the reaction and decide it's SN1 or SN2. You kind of have to take the whole picture into consideration. If you have a secondary halide, you really can't decide whether it's going to go SN1 or SN2. It could do both. Same thing for primary or secondary halogens. So this is a primary but with resonance, right? Because it's allylic, or a secondary with resonance. It's tough to say. It could undergo both SN1 and SN2. So what do we do in those cases? Well, we have to, again, step back and consider the whole word problem, right? The whole picture. So what we were doing in that previous slide was we were looking first, which I think is the first thing you should do, is look at the structure of the halide or the electrophile. It's not always a halogen, as you saw. It could be an alcohol that we protonate. So you want to look at your electrophile. Is it primary, secondary, tertiary, allylic, vinylic, right? That's going to help you. And then once you figure out that, it's in the middle ground, I need more information, you want to start considering all those other effects. You want to consider the reactivity of the nucleophile, right? And there's a couple things that go into that. The strength of the nucleophile, right? Is it negative or is it partially negative? And also the size. Is it bulky or is it small? Okay, so those are your considerations for the nucleophile. If it's strong, it's going to favor SN2. If it's weak, it might favor SN1. If it's bulky, it'll favor SN1 because, you don't want sterics when you're doing SN2. The other thing, if it's given, is the concentration of the nucleophile. Okay? That could help you as well. It's not always given though, so, it's something to consider. And also the solvent in which the reaction is carried out. I think solvent effects and the type of nucleophile are the things that I would shoot for before anything else. After, of course, looking at your electrophile. But, are you dealing with a protic solvent, which favors SN1? Or are you dealing with an aprotic solvent, polar protic solvent, which favors SN2? Retrieval cues and critical skills for this chapter seem short. However, they are challenging and you need to practice writing the mechanisms. I can't stress that enough. When I say SN2, you've got to be able to completely begin writing an SN2, know how to push the electrons to do an SN2 protocol. It's, I don't want you to, if I told you 5 plus 3, I want you to know what to do. I don't want you to go, addition. Yeah. Is that putting things together or taking, no, there's no waffling, right? SN2 is a critical skill. SN1 is a critical skill. When in the future, we're going to be saying, oh yeah, this reaction undergoes an SN2. All that goes along with it, I want you to learn so that you can do that function on any molecule that can undergo an SN2. So I need you to be able to write the story, write the electron pushing story when I tell you to do an SN2 or if I tell you to do an SN1. Now, for some practice problems, the remainder of these PowerPoint slides are practice problems for you. And I'm just going to show you again so that you can see my walkthrough of a problem set. So if I was given these two reactions, let's say I was just given reaction A, okay? Reaction A can be written a lot of different ways, okay? It could be written like this. Okay, it could be written like this. It could have the sodium methoxide and the alkyl halide, with a plus sign between them, right? Kind of like your equation. Regardless, these all ask you to do the same thing. How and where they are, whether they're over the arrow, under the arrow, if the two reagents are written before the arrow, or swap the reagents, right? Put the NaOMe over here, and then maybe this is less traditional because we're organic chemists after all. We always feature prominently the organic molecule, right? So although there's nothing wrong with putting the organic molecule over the arrow, it's just not the traditional way to do it. We usually put our non-organic or the reagent from a bottle that's less complex. The one that we're interested in using as the reagent, and we're trying to follow ultimately the progress of this carbon-based molecule. That's the molecule of interest. So if I'm given that, I want to take a step back and look. I see, all right, first off, there's a bromine, right? There's your bromine. It's an alkyl halide. It's the only functional group on my organic molecule. Identify the functionality. Now you bring yourself into chapter 7. You say, I know that I can do stuff with alkyl halides. I've done stuff. You can do SN1 and SN2. Okay, so now you've got some functions to perform. You've got like SN1 or SN2, but which is it? Next, you look at the electrophile. This is the electrophile. It's your alkyl halide. Is it primary, secondary, or tertiary? And you look at it and you're like, okay, it is secondary. Oh, darn it. It is in that group. It's not primary and it's not tertiary. It's not in that group that's easier to decipher. It's right in the middle of the road. So I have to look outside of the electrophile to the nucleophile. And the nucleophile is O minus CH3. Or it could have been given to you as NaOCH3 or NaOMe. We don't buy O minus in a bottle. It comes with a counter ion as a salt. So let's say I look at the nucleophile and I see in this case it's given as O minus or sodium O minus. This is strong. It's a strong nucleophile. So the nucleophile is in charge. So that's where you're going to start your pen. Oh, get it? It's in charge. It's got a charge. So that's who you should focus on. The nucleophile's in charge. It's going to do what it needs to do, which in this case is SN2. God, I'm even rhyming in this. So there's my electron pushing. The electron pushing tells the game. So what I did is I went to the nucleophile. I saw that it was both strong and did you also notice that it's small? It's a small molecule. So I say, this is what I'm going to do. And then I do it. I push the electrons and I draw the result of that push. Backside attack, one concerted mechanism. So that means that it came in from the back. The hydrogen got pushed forward. The OCH3 is now in the back. You can see it might have been a little easier to write using the above diagram. Either way, they're the same molecule. And there you go. Had I been given the second reaction on its own, it's actually the same electrophile. It's a secondary halogen, secondary bromide. So I'm in that in between. So I have to look at the nucleophile. The nucleophile is strong, but it's weak in this case. So the nucleophile is weak and small. But the weakness of it is what stands out to me, right? The fact that it's weak means, and it's protic, right? It's also protic, serving as a protic solvent. Sodium methoxide in the previous case is a salt. It's a solid. It's not my solvent. In fact, the solvent is not given in the A scenario. In the B scenario, the methanol is probably acting not only as the nucleophile, but as the polar protic solvent. And so I know that this is most likely to undergo SN1. The leaving group leaves. I'm going to draw it like this. Carbocation forms on the second of the butane. I stop. Look around. Can I do better than a secondary carbocation intermediate? Nope. To the left would be primary, to the right would be secondary. There's no need to move, so it's going to stay put. Now I finish up. Second step, after solvolysis, front or backside attack, I can make methoxy from one side, methoxy from the other side. After I work it up using some acid-base chemistry, work it up and remove those extra protons. Probably have to toss in a little bit of base in there to pluck off those extra protons. Now I'm going to get two products. And these happen to be ethers, methoxy ethers. And they are a mixture of, let me take a look, one stereocenter, complete inversion between the two. So this is a mixture of enantiomers. So if I did this SN1 reaction on an enantiomerically pure starting material, I would end up with an enantiomerically racemic mixture. I killed my beautiful stereocenter. However, in the other case, I didn't kill my stereocenter. I inverted it though. It went from R to S. So this is the approach. You kind of methodically want to look at all things. Sometimes just because the electrophile is one thing doesn't mean you shouldn't look at the nucleophile. Don't ignore stuff. To kind of go through the process, check the electrophile, check the nucleophile, what solvent are they using. You kind of have to assess the whole situation in order to make a good educated response for which mechanism you're going to employ. So I leave you with the remaining practice problems for you guys to try. And that's going to cover a bunch of different opportunities for you to practice your electron pushing, to practice determining product distributions, and also to, given the product, given maybe an unfamiliar set of reagents or a set of reagents that you think might go one way, you might be surprised. What if you're given the product and you're asked to determine what type of mechanism it underwent? This last set of problems is really good with that.